started to be respectful of everyone's time. So welcome everyone. My name is Andrea Arias. Today we have our Informs RAS International webinar, and this is the 13th of the series we have had so far. And we are very excited today because we have a very special guest. His name is Roger Baugher, and he's an independent consultant. He has worked in the rail industry for over 45 years and, very, very wide range of responsibilities. He has a master's degree in civil engineering from the University of Illinois, and also has an MBA from Northwestern University in transportation and finance. He has, as I said, a very extensive career in the railroad industry. He has worked at 4 railroads, and among the areas he has worked on, there's service design, equipment management, system analysis, line capacity, and many others. He introduced and implemented algorithmic blocking at NS, Norfolk Southern, which is a concept that has been adopted by half of the railroads in the US and Canada. Roger has also contributed chapters to 2 railroad handbooks. And so today he works as an independent consultant. And I'm so happy to have you here. Thank you so much for sharing your knowledge with us. And so this webinar will be recorded. You will receive an email with the link to watch the recording, and the slides will also be shared. We have a chat in the Zoom, and so if you have any questions during Roger's presentation, please feel free to put them on the chat, and I will read them after he finishes his presentation. We will have some time at the end for Q&A, so but please do not interrupt the speaker while he's presenting. Okay, so without further ado, I will leave you with Roger. Thank you so much.
Well, thank you for the introduction. Is everyone seeing my happy smiling face there? Very good.
Yes.
So in the 45 minutes or so of my presentation, I hope to accomplish or cover these areas, take a quick look at yard models to which I'm aware. I am going to tell you this is not an exhaustive study. There's many things that I probably was never exposed to, but I'm trying to hit the highlights of ones that I know reached a certain level of acceptance and use. A brief description about yard design, how it impacts simulation work, discuss why I chose AnyLogic for the yard modeling efforts I'm doing. I'll be demonstrating 3 yard models today. I'll present the first 2, then take a little break to talk about where we stand on operations research efforts, then demonstrate the final model, and then discuss possible next steps and response to questions and comments. So Andrea covered a number of the things that are in this. As she said, I worked in transportation department staff at 4 railroads, but I was never really specifically tied to yard operations. I was always in a staff function. I worked with models that touched on yards. Network flow models obviously focus on flows through yards, and line of road dispatch focuses on their interaction with line of road operations, but neither of these actually dealt in any detail with yards, and they treated yards largely as black boxes. When I was in service design at BNSF, there was a yard in South Texas, which was having troubles doing the switching required to support the chemical plants in the vicinity. And based on some efforts that I put into developing yard analysis and visualization tools, I soon came to realize that yard simulation could provide needed functionality in at least 3 areas: problem solving, capital project justification, and training. Problem solving too many times I've been in morning meetings where there was a lot of finger pointing, and rarely was there a resolution of the problem. What if we could actually go into figuring out what went wrong in a particular yard yesterday and figure out how we might do it differently? Was there anything we could have done that would have predicted where we are today? Capital project justification. It's really difficult, I think, to justify even a simple thing like a crossover in a yard, because there just aren't tools that help you do that. In training, we just don't have the training environment you once had. Effectively, when you were a new employee, you apprenticed to more senior people, and frankly, those senior people are retiring, and we have smaller crews, so there's not the opportunity to pick up the skills to do the job as well as it needs to be done. So my goals today to explore where we stand and advocate for both yard simulation and for intelligent yard command systems to play a role in better managing flat yards. And I want to encourage feedback on the ideas that are presented here. So here I have a yard model timeline. This is definitely a very high level. There's many developments that I have not covered, but my point here is to focus on those that have been implemented at railroads and that have had reasonably wide use. So I picked the date July 4th, 1828. That was the day of the first stone was laid for the B&O Railroad, which was the first common carrier railroad in the United States. And ever since, railroads have had to design yards relying on manual analysis, and that process has improved with the arrival of computer spreadsheets, but fundamentally hadn't changed conceptually since July 4th, 1828. In 1970s, the decade of the 1970s, Penn Central went bankrupt in 1970. The government set up the mechanism to create Conrail. Rock Island and Milwaukee Road were in trouble. So there was demand for network rationalization tools. These also touched on some areas of yard performance. In that decade, the Department of Transportation and the FRA were created. That provided funding, and that funding produced a flurry of academic and industry research efforts. Also coming out of that was a service planning model and the automated blocking model, both of which focused on yards, but again, the specifics of how the yards worked was not modeled. The first time in my knowledge that there was a model that got into the details of yard operations and actually at a railroad was at CN in the 1980s. This model was later shared with CSX. It's called the Terminal Interactive Model, or TRIM, and it involves a loop. Effectively, the computer provides the status information and plays out any commands that are provided to it. And you have a large team, I'm told between 8 and 20 people of field and operating officers and staff that specify the switching commands. So you'd start with an initial condition. The computer would say, this is the way the yard looks. Then this team of people would say, well, the next move to do is such and such. That was fed into the computer would play it out, give an update on the status, and this process repeated until the study period was completed. As you might imagine, this is a very slow process. I'm told it took 3 times real time or 24 hours clock time to simulate one 8-hour shift. And due to the labor intensive nature, it's not repeatable. If somebody said, yeah, but on Wednesdays, this train runs, you're not going to get back into this thing. So in the 1990s, multi-rail and rail traffic controller emerged, widely implemented. Again, both touched on yards, multi-rail flowing traffic through yards, rail traffic controller interacting with yards, but neither actually dealing with how the yard specifically did its work. In 2000s, Norfolk Southern devised two terminal models, one for Decatur, Illinois, the entire terminal. That was written in AnyLogic, and I believe that Decatur, Illinois is the largest flat yard in North America. Also in the 2000s, Yard Sim was developed at Norfolk Southern. It was written in Java, and it used open source process flow and rule engine to implement operating and scheduling strategy. So based on that description, I don't know that it was an optimization, and I think it was a set of rules as to what should be done. Optim developed a hump yard simulation system in the 2010s, implemented at 6 hump yards on CSX. It was later implemented on the Belt Railway, and those of you who know Tyler Dick at University of Illinois know that he has access to that model, and that's the source of a lot of the analysis that he performs on yard performance. Also in the 2010s, GE and later Wabtec began the development of Yard Planner. It's initially focused on hump yards, but there's work on a flat yard version. And effectively, this is a system to automate the workflow through the yard. A yard takes a lot of coordination. So this automates that and obviously makes a plan and executes the plan. Thames introduced Switch It, which is an Excel-based simulation, worked with Jeremiah Dernberg at CSX to analyze alternative switching arrangements. And also in the 2010s, Transsystem Corporation, of which I am a part-time employee, developed something called Transportation Modeling Studio. To my knowledge, and I'm not, I haven't been shopping, so I don't know, but it's, I'd certainly say one of, if not the only general purpose railroad terminal simulation model that I know. It's built in AnyLogic, and it's been applied to hump yards, flat yards, intermodal facilities, industrial facilities, and ports. I myself was involved with this tool in 2 hump yards and 4 industrial facilities. Also in 2010s, I started tinkering with yard visualization and yard simulation. The output of some of that effort you see to the right here. This is the inventory at Argentine Yard in Kansas City on BNSF. There are 60 class tracks, and the track length and the car length are to scale. So we see a track number. This is the free space in feet, free space in cars, and then this is the number of pin pulls in that track. Now you would hope, since this is actually after switching, that the number of pin pulls is 0, and for the most part they are. But this track I would believe to be a rehump track, a slough track, because it in fact has 3 pin pulls in it. This tool was set so that you could click on a track and get the information on the track. You click on a car and get the information on a car. And then there were general purpose filters like show me where all of the empties are, where all the hazmats are, where all the cars are at set more certain length of time. And as you can see, this is the status of a particular date and time at Argentine. So the common challenges, all these models, they're proprietary, takes a large effort to integrate with the railroad information. And let's face it, they're just damn complicated because frankly, flat yard themselves are complicated. And flat yards vary so greatly in layouts, tasks, staffing levels, deployed technology, and so on. And I think one of the most important challenges is that yard data systems do not capture the detailed operations in a flat yard, only the inputs and outputs. Much of the detailed knowledge is in the heads of the yard officers, especially the yard masters and the yard conductors. What I want to point out here is, let's say, for example, a yard job comes on at 8 a.m. They're given a switch list based on the inventory that stands at 8 a.m. They go out, they switch for 4 hours, they come back, said, job accomplished, we're done. So first, now you're assuming that they did everything you told them to do. But in any case, you give this back to the yard clerk who updates the inventory. How did car 7 get into track 3? I have no idea. What was the sequence? So the detailed knowledge about how anything was accomplished is not captured by the yard systems. So I just want to take a quick look at yard layouts and how they also make the simulation of yards complicated. This is a layout you would see typically at a hump yard, but there's no reason flat yards couldn't also have this. In any case, you have a dedicated receiving area, a dedicated departure area, and you have the bowl tracks where you are sorting the cars. It's a one-directional process. You don't receive here. You don't depart here. Everything has a dedicated function. Say it's one directional, and frankly, it's an outdoor factory. What receiving does is the same day in and day out. And you won't have trains arriving and departing from a class track. They'll arrive and depart from these other tracks. So there's a fixed function for each part of the facility. Let's compare that to some flat yard layouts. Now, this is the simplest flat yard layout. It's a stub end yard. You'd see this maybe in industrial facilities, storage and transit facilities, and so on, where you're basically holding cars for later use. This is a layout of a yard that was designed in 1993 for the Santa Fe in Alliance, Texas. It has the advantage that all the tracks are the same length. It has the disadvantage that all the tracks are the same length, because if you have a long block, you have to put it on 2 tracks. If you have a short block, you're using up an entire track, whether you need it or not. The way this operated, cars would be shoved in from the rest of the yard here into a track here. A yard engine would come here, grab those cars, kick into these various tracks, and then before the train is scheduled to depart, the yard job would come in, grab the appropriate cars from the tracks and pull out this way. The most significant thing, I think, about the layouts of flat yards is what the relationships with the main line is. What you see here is a 10-track yard where the main line skirts the outside of the yard. So here, through trains can bypass the yard and not touch, not interfere with the activity going on in the yard, unless that train has work to do, setting out or picking up cars. In that case, you're now arriving or departing cars or trains on what could potentially be the sole switching lead. So in any case, you're going to have disruption of switching activities while you arrive and depart trains. Also, in this kind of a layout, there's no dedication. This track is not necessarily always for receiving, and this is not always for departure. The yard tracks are pretty fungible. So that adds an extra level of complexity. This is perhaps one of the most challenging yard layouts. Here we have a main line going through the middle of a yard. Functionally, we now have 2 yards. If the main line is congested, if there's many trains that are coming through here, then you effectively have 2 separate yards that have to communicate with one another, but only have certain windows to do such. Let's say, for example, that we build westbound blocks here and we build eastbound blocks here. So we have a train that comes in, it's going to have a mix of westbound and eastbound cars. So if it has more westbounds and eastbounds, okay, we'll put it in here. So we'll switch it up, and it's great. We've got the westbounds here, but we're going to do the eastbounds. Oh, okay. Well, I've got to put them into what's typically called a slough train. So I'm going to shove them into a track for transfer at my convenience, possibly once a shift, to the other side. Okay, so now I've dedicated a track. I've switched it once. Now, when there's an opportunity to cross over, I pull that track, and now I shove in, and there's a slough track over here for cars going this way. So now that car has to be switched a second time. So this is probably one of the more challenging ways to operate a flat yard. So I see railroad yard simulation as basically have two elements. One is a simulation and one's a command and control. We kind of saw this with trim, that the simulation provides outputs and receives inputs, and it simulates those yard events that we specify. And the command and control says which tasks to perform, when to perform them, and what order to perform them. So when I was looking at what software I thought would best support the switching operations, I found AnyLogic. It was the only package that I saw that had modules specifically addressing railroad infrastructure and operations. The software got its name because it supports three simulation paradigms: discrete event and agent-based, both useful for railroads. System dynamics, not so much. You can use multiple paradigms in the same model. Now, if we were just running a dispatch model, we would use discrete event. We'd say at this time, this train departs and it runs at this speed, and so it'll arrive at a specific time. But let's say we want to consider modeling a PTC system. Okay, so we dispatch the trains, but what we're really interested in is how the locomotives can talk to the wayside devices to update their information and to operate safely. So what we do is we treat the locomotives and the wayside devices as agents. And once they're in relative proximity, which is something you can specify, they can now communicate. So here we have a mix of discrete event and agent-based in a very productive form. So quickly, AnyLogic rail library is powerful but very complex. It understands the elements of railroad operations. To date, I've not encountered any situation that cannot be modeled. I won't say it can be modeled simply, but I say it can be modeled. AnyLogic has been widely installed at Class 1s in the US, and the support is quite remarkable. I've sent models that don't function correctly, not syntactically, but just not logically, and they debug them and return them correct. So I don't know too many companies that provide that level of support. Just a quick look at the rail library. Obviously, we can create trains and rail cars. We can add great detail or little detail depending on the application. This is where we define the track. Here's where we originate and terminate trains. Similarly, here in enter and exit is originating, terminating trains. We have couple and decouple, and we have this one module that's quite remarkable. It's very powerful, and it's used to move a train from an existing location to a target, or it can follow the existing switches. You can route to a target specified, or it can calculate a route based on shortest path. It will throw the switches as necessary, if so required. The shortest path can specify tracks to be avoided or identify avoid conflicts. You can move to a set location and offset on a track, or a specified distance. The specified distance can be just past a switch so that you can do a pull and shove. It sets acceleration, deceleration speeds. So it's a very remarkable single block of logic. One of the things I like about AnyLogic is you develop the models graphically, and then you have sort of a self-documenting document. I won't get into anything in great detail, but let's say we have a train with the locomotive, which you'll see later. And so it comes, the first thing it's going to do is it's going to uncouple from cars on that track, or not uncouple, depending. It will now pull ahead, and then it's going to shove. So it can shove to a couple where a track's occupied, or it can shove to empty where a track is empty. Let's start with the empty. With the empty, it comes here, and it's ready for the next move because it doesn't have to couple with anything. Here, it's going to couple with cars. So it comes here, and this couple has all the other tracks that have cars, and it figures out that this move is coupling with cars on a standing track. It builds out of two, it builds one. And here we decide, are we going to shove in the track, or are we going to pull before uncoupling? And then we get to the next move. So I basically described to you the underlying logic. Now, I won't say there's not a lot of code that specifies exactly what's being done in each of these steps, but logically, I can say this is how this model works. So we're going to do 3 models I'm going to demonstrate, and each uses a different method to specify the sequence of switching events to be executed. First, we'll start with manual entries. Then we'll do entries based on observation, where I replay actions from a rail yard, and then entries from OR and AI algorithms to replay a recommended sequence. So what you'll see in this demo is basically I will specify which cars are on which track and the initial location of the switch engine, specify the sequence of pull and shove events to be executed, and then keep track of the number of moves and the time consumed. Oops, hang on. There. So hopefully everyone's seeing, is everyone seeing the model?
Yes.
Okay, excellent. So what I've done is I've already specified the layout of the tracks. So this train, here's the locomotive, and here's the cars on track 2, here's the cars on track 1. The objective is to build an AA, BB, CCC. I'm going to build it on track 2. Here's the total process time. So the first thing I'm going to do, and I've got to check my notes here, is I'm going to pull one car from this track, and I'm going to shove to this track. So I click on this. The motion is actually based on speed and the layout of a yard. So I'm speeding it up so that it doesn't take a really long time. So next thing I'm going to do is I'm going to pull 6 cars. So 1, 2, 3, 4, 5, 6. And you can already see that I am going to be able to have an A, B, B, C, C, C. So I don't have the A, but I have the rest. I need a second A. Okay. Now I'm going to pull 4 cars. So I'm going to get these cars out of the way. 1, 2, 3, 4. And I'm going to shove back to track 1. And I think you can see where we're going here. Okay. So now grab this guy, and I shove him back to track 2. Okay. So that was 4 moves, and it took 6 minutes and 4 seconds. Okay. So what have we learned from that experience? It can serve as a simple yard design tool. We can really scrutinize what switching policies have been used. We can use it to work with personnel that need training or retraining. We can start build a relationship between, quantify the relationship between switching sequence and time consumed. And we can introduce factors that typically aren't considered in yard performance, things like pin pull count, how messed up is the inbound train, and blocking complexity, how difficult is it to build all the blocks. And it can be used to demonstrate the need for additional track or crew resources. So my next model is one based on actual simulation, or based on observations of a yard. We've captured rail car position from yard inventory. We've captured actions from video camera, convert the actions to commands, we simulate the commands, and we calibrate the model against reality. So now what to look for here? Let's see, I need to get, hang on. I need to get the next guy set up here. Okay. Back. Okay. And back. Oh my gosh. Okay. So what to look for here? Hang on while I swap my car. There's, I think, a lot to learn from the practices as a very experienced crew. Watch for the crew's pre-planning. They're not just making this move, they're planning 3 or 4 moves ahead at least. So note that the tracks are shoved clear to make space for cars that are going to be kicked later. Observe the cut cars are pulled to the clearance point. So basically, instead of uncoupling and pulling ahead, you pull ahead and then uncouple. It lessens the travel distance for subsequent pulls, and it positions the ground crew adjacent yard ladder for subsequent moves. Note that spare tracks are also used temporarily to hold cars, and note that nearly all moves involve kicking cars, and very few are actually shoved to rest. So just wanted to quickly show how well AnyLogic can visually compare with the actual operation. This is obviously a snapshot taken from the yard video, and this is the same move being done in the model. Okay. And it's cranking. Okay, so this starts. Oh, I want it. Okay, this starts in a 2D model. This is typically a good way to view the operation yard as a whole. There's an issue right now with the way it's representing rail cars. So the 2-dimensional is not as good as the 3-dimensional for this particular purpose. It is a problem there AnyLogic's aware of and they're working to fix. So instead, let's look at this view. So obviously you see the switch engine coming in, and you'll notice that when it's coupling to existing cars, there's a short delay. It stops about 30 feet from a car to allow the ground crew to get the couplers aligned and to observe that the couple worked correctly. So there's another pause. Now, you would think, okay, I'll just shove this until it's clear of the ladder, but instead you see he's actually shoving deep, and that's because he's going to kick cars into there at a later date. He's doing the same thing here. This is another track where he's going to kick cars in later. So now he's got this long cut. You can see the different color cars. Theirs are not necessarily blocks. I couldn't get a clean definition of blocked track. So what I did here was I just specified a color based on the tracks they're going to. Now, in kicking, there is a science to it. You can't kick a car unless you know the car ahead has cleared, because otherwise, if it derails or if it fouls the ladder, then you'll have a collision. So there's a timing factor there as well. So now he's pulling a really long cut, but he didn't pull the whole thing. You can see he could have pulled and gotten these cars, but you want to try to minimize the number of cars you're pulling at one time. You notice there was quite a long kick there. There is a restriction typically on how many cars you want to kick at one time. And it's probably dependent on loads and empty mix. So now he used this track as a temporary holding because he needed these cars to be separated from these cars, probably because these were hazardous material or something like that that needed to be away from the head end. So from that, I think we can identify the factors that led to poor yard operation. I didn't see any, but in other videos, I'm sure we capture inefficient switching practices, inadequate staffing levels, conflicts with inbound, outbound trains, yard volumes, how yard volumes and block counts affect things, and then maintenance issues. Something was was in bad order status. We can document the need for additional track or crew resources. And unfortunately, usefulness is limited by inability to easily capture switch movements for input to the simulation. Frankly, it took me days of moving forward and back through the video to understand what moves were done. That's in part the current camera's low resolution. There's a new one in place. And frankly, the location of the camera is not at the yard throat, it's further along, and so there's activity that goes on behind. In any case, something needs to be done to capture switch moves. So just real briefly, and this is not statistically significant in any way, this is just a set of observations. Here's the number of moves that were captured in the video. Here's the time in the video. Here's the time in the simulation. You can see in total, the times are quite remarkably the same, but then you can see on individual moves, they can be quite different. So I don't know if this is the law of large numbers or something else is working here. I never took the time to completely understand why these discrepancies. Sometimes, obviously, I assume a certain speed for the locomotives. It's not sensitive to the horsepower and the weight of the cars. So acceleration, deceleration, maximum speed might be different. Sometimes the cars are not at the clearance point, they're further in, so there's more travel and so on. But in any case, I was heartened by the fact that we're in the ballpark. So we looked at 2 of 3 ways to specify a sequence of switching events to be executed. And now let's look at the third. So I just want to take a quick sidebar to look at OR algorithms for yards. In the years that I've been attending RAS meetings, I've heard about inbound train sequencing, hump sequencing, block to track assignment, pull down and train assembly. But frankly, that list does not cover what's needed in a flat yard, which is understanding, specifying, and executing a sequence of switch moves needed to sort cars from inbound trains to build outbound trains. So to my knowledge, little attention has been focused on analyzing or optimizing switch movement sequence for flat yards. And this occurs at a time when gentlemen like this, who've been working in the railroad and have been switching for 30 years, are retiring, and they're replaced with people that we hire from the streets and who cannot understudy these gentlemen because they're no longer there. So let me introduce Cedar AI. Most people know the company. They've been supporting RAS for some years, and in fact, they're a sponsor for this webinar. Anyway, several years ago, 3 former members of Amazon Web Services formed Cedar AI to apply their skills to analyzing and improving the performance of transportation networks. I've been involved with them as a road advisor for several years. When I started, they had about 5 people, and now they're up to about 20. They have 2 primary products, ARMS, which is an inventory management system that is targeted for short lines. It's been adopted by the TRA for the switching, a switching company there. There are other switching companies may be clients in the future. And there's also the focus of what we're discussing today is Optiswitch, which is an AI-based system to sequence switch movements to best meet an objective. Okay, so here's the final demo of today. And let's see here. So we're going to select a JSON file, and we're going to observe the number of moves and the other operations that are displayed here. Okay, so as you can see, obviously we have the same layout as we had before, but in this case, the instructions are going to come from a text file, a JSON file. So what we see here is the same objective we had before. We're going to build on target track 2. We're actually going to use 3 tracks. So this number is inaccurate, and it's going to have a total of 3 moves. So we're going to pull 1 car, pull 9 cars, pull 6 cars, and so on. Again, I'm going to speed it up. Here's the total process time, and then here's the time for each one of these steps. So you can see we're building it differently than before. We're taking the cars at the end. And in fact, oh my God, we got the AABB-CCC already. We put the train away, and in 3 moves and 5 minutes and 45 seconds, we completed the same task that took longer with the other approach that we used earlier. So let's look at what we can take away from that. It provides a visual check. We often have an issue where an algorithm comes up with an idea that just doesn't make any sense. So this is a good visual check. We can generate estimates of the time required to execute a recommended sequence, because our job is to minimize time, not the number of moves. We start to understand relationship among time, moves, tracks used, number of cars pulled, etc. And we can start to identify and quantify constraints that may have not been considered. How long is the switch lead? Maybe sometimes you can use the main. And if you can use the main, you can pull more cars. Perhaps the power of the locomotives is not adequate. So that'll have an impact on acceleration, deceleration. Some we haven't touched on at all is time required for the ground crew to walk. One of my next steps is to start figuring out what the impact of the crew's walking has on performance. Impact on different crew sizes and remote control locomotive operations, and the randomness of the car sort order on incoming trains. So here's the output from 4 runs, or I should say from a run with 4 alternatives that were considered, all of them reasonable. Number of moves varied from 3 to 5. Number of tracks used varied from 2 to 3. Here you can see the best times were under 6 minutes, and the worst times were under 9 minutes. So we're talking about a 50% difference. Now over here is the number of cars pulled. If we have a locomotive with inadequate power, then the acceleration will be diminished, and so the number are longer, the larger number of cars pulled, the slower. Also, if you're concerned about carbon footprint and so on, you're better off just pulling 9 cars if possible rather than pulling 15. So just touch on where I think Optiswitch and similar systems can do. It can provide benefit. Consider that instead of being in somebody's head, we now have a detailed computer-based switching plan that knows what the yard will be doing in the next shift. And so hours before train departure, the cars expected to depart on an outbound train will be known, or at least a reasonable estimate, and that can inform downstream yards and trip planning systems. And it can be run in real time and can react to changes in the yard. I see the real benefit here is from better exchange of information between yards. Today, if a downstream yard is in trouble, it makes a phone call to an upstream yard and said, can you help me out? And the upstream yard may or may not even consider it. In the future, the requesting yard would know what the upstream yard's plan was. They could negotiate the alternatives. The upstream yard would have what-if capabilities to say, oh yeah, I can make an extra block. That'll take me an extra 15 minutes. Oh yeah, and I can do that. So possible next steps as I see it, extend this to industry switching instead of just terminal switching, develop a training package, develop general purpose yard analysis tool, integrate with Optiswitch, and develop some data capture systems. My idea basically is, can an array of cameras and sensors employing low-cost components automatically update yard inventory as switching progresses, flagging switching errors that when they occur? We just don't know how many times when you're flat switching, the person put 2 cars in instead of 1 or put it into the wrong track. So this is an area I'm researching, and I have some tools under development. 2 books that OR professionals should know about. The one on the left was put together by people on this phone call largely. It is a qualitative rather than quantitative description of OR. There's not a lot of formulas, but the intent is to basically say these are the approaches that have been used. This is a more recent book. As you can tell from the names, it's European based. And in any case, I think both of these books could be useful as you hire OR people to introduce them to what a trip plan is and the like. So here's my concluding remarks. I appreciate your attention. I provide the contact information. I see from the clock here that perhaps I ran a little long. And in terms of questions, it occurs to me that I know that Dr. Pepper has 23 spices. V8 has 8 vegetable juices, and preparation H has at least 8 preparations. But don't ask me what blended 33-to-1 impact blue ribbon is. So that's all for me.
Thank you so much.